Concrete is a composite material composed of aggregate bonded together with a fluid cement which hardens over time. Most use of the term concrete refers to Portland cement concrete or to concretes made with other hydraulic cements, such as cement fondue. However, road surfaces are also a type of concrete, asphaltic concrete, where the cement material is bitumen. In Portland cement concrete, when the aggregate is mixed together with the dry cement and water, they form a fluid mass that is easily molded into shape. The cement reacts chemically with the water and other ingredients to form a hard matrix which binds all the materials together into a durable, stone-like material that has many uses. Often, additives are included in the mixture to improve the physical properties of the wet mix or the finished material. Most concrete is poured with reinforcing materials embedded to provide tensile strength, yielding reinforced concrete. Famous concrete structures include the Hoover Dam, the Panama Canal and the Roman Pantheon. The earliest large-scale users of concrete technology were the ancient Romans, and concrete was widely used in the Roman Empire. The Colosseum in Rome was built largely of concrete, and the concrete dome of the Pantheon is the world's largest unreinforced concrete dome. Today, large concrete structures are usually made with reinforced concrete. After the Roman Empire collapsed, use of concrete became rare until the technology was redeveloped in the mid-18th century. Today, concrete is the most widely used man-made material. History. The word concrete comes from the Latin word concretus, the perfect passive participle of concrescere, from con and crescere. Prehistory. Perhaps the earliest known occurrence of cement was 12 million years ago. A deposit of cement was formed after an occurrence of oil shale located adjacent to a bed of limestone burned due to natural causes. These ancient deposits were investigated in the 1960s and 1970s. On a human timescale, small usages of concrete go back for thousands of years. Concrete-like materials were used since 6500 BC by the Nabatarar traders or Bedouins who occupied and controlled a series of oases and developed a small empire in the regions of southern Syria and northern Jordan. They discovered the advantages of hydraulic lime, with some self-cementing properties. By 700 BC, they built kilns to supply mortar for the construction of rubble wall houses, concrete floors, and underground waterproof cisterns. The cisterns were kept secret and were one of the reasons the Nabatarar were able to thrive in the desert. Some of these structures survive to this day. Classical era. In both Roman and Egyptian times it was rediscovered that adding volcanic ash to the mix allowed it to set underwater. Similarly, the Romans knew that adding horsehair made concrete less liable to crack while it hardened, and adding blood made it more frost-resistant. Crystallization of stratlingite and the introduction of pyroclastic clays creates further fracture resistance. German archaeologist Heinrich Schliemann found concrete floors, which were made of lime and pebbles, in the royal palace of Tiryns, Greece, which dates roughly to 1400 to 1200 BC. Lime mortars were used in Greece, Crete, and Cyprus in 800 BC. The Assyrian Jerwin aqueduct made use of waterproof concrete. Concrete was used for construction in many ancient structures. The Romans used concrete extensively from 300 BC to 476 AD, a span of more than 700 years. During the Roman Empire, Roman concrete was made from quicklime, pozzolana and an aggregate of pumice. Its widespread use in many Roman structures, a key event in the history of architecture termed the Roman Architectural Revolution, freed Roman construction from the restrictions of stone and brick material and allowed for revolutionary new designs in terms of both structural complexity and dimension. Concrete, as the Romans knew it, was a new and revolutionary material. Laid in the shape of arches, vaults and domes, it quickly hardened into a rigid mass, free from many of the internal thrusts and strains that troubled the builders of similar structures in stone or brick. Modern tests show that opus cementitium had as much compressive strength as modern Portland cement concrete. However, due to the absence of reinforcement, its tensile strength was far lower than modern reinforced concrete, and its mode of application was also different. Modern structural concrete differs from Roman concrete in two important details. First, its mix consistency is fluid and homogeneous, allowing it to be poured into forms rather than requiring hand layering together with the placement of aggregate, which, in Roman practice, often consisted of rubble. Second, integral reinforcing steel gives modern concrete assemblies great strength in tension, whereas Roman concrete could depend only upon the strength of the concrete bonding to resist tension. The widespread use of concrete in many Roman structures ensured that many survived to the present day. The baths of Caracalla in Rome are just one example. Many Roman aqueducts and bridges such as the magnificent Pont du Gard have masonry cladding on a concrete core, as does the dome of the Pantheon. Middle Ages after the Roman Empire, the use of burned lime and pozzolana was greatly reduced until the technique was all but forgotten between 500 and the 14th century. From the 14th century to the mid-18th century, the use of cement gradually returned. The Canal du Midi was built using concrete in 1670, and there are concrete structures in Finland that date from the 16th century. To create this structure, between 1756 and 1759, British engineer John Smeaton pioneered the use of hydraulic lime in concrete, using pebbles and powdered brick as aggregate. A method for producing Portland cement was patented by Joseph Aspdin on 1824. Reinforced concrete was invented in 1849 by Joseph Manier. In 1889 the first concrete reinforced bridge was built, and the first large concrete dams were built in 1936, Hoover Dam and Grand Coulee Dam. Composition of concrete. There are many types of concrete available, created by varying the proportions of the main ingredients below. In this way, or by substitution for the cementitious and aggregate phases, the finished product can be tailored to its application with varying strength, density, or chemical and thermal resistance properties. Aggregate consists of large chunks of material in a concrete mix, generally a coarse gravel or crushed rocks such as limestone or granite, along with finer materials such as sand. Cement, most commonly Portland cement, is associated with the general term concrete. A range of materials can be used as the cement in concrete. One of the most familiar of these alternative cements is asphalt. Other cementitious materials such as fly ash and slag cement are sometimes added as mineral admixtures, either pre-blended with the cement or directly as a concrete component, and become a part of the binder. For the aggregate, water is then mixed with this dry powder aggregate blend, which produces a semi-liquid that workers can shape. The concrete solidifies and hardens through a chemical process called hydration. The water reacts with the cement, which bonds the other components together, creating a robust stone-like material. Chemical admixtures are added to achieve varied properties. These ingredients may accelerate or slow down the rate at which the concrete hardens, and impart many other useful properties including increased tensile strength, entrainment of air, and/or water resistance. Reinforcement is often included in concrete. Concrete can be formulated with high compressive strength, but always has lower tensile strength. For this reason it is usually reinforced with materials that are strong in tension. Mineral admixtures are becoming more popular in recent decades. The use of recycled materials as concrete ingredients has been gaining popularity because of increasingly stringent environmental legislation, and the discovery that such materials often have complementary and valuable properties. The most conspicuous of these are fly ash, a byproduct of coal-fired power plants, ground granulated blast furnace slag, and silica fume, a byproduct of industrial electric arc furnaces. The use of these materials in concrete reduces the amount of resources required, as the mineral admixtures act as a partial cement replacement. This displaces some cement production, an energetically expensive and environmentally problematic process, while reducing the amount of industrial waste that must be disposed of. The mixed design depends on the type of structure being built, how the concrete is mixed and delivered, and how it is placed to form the structure. Cement. Portland cement is the most common type of cement in general usage. It is a basic ingredient of concrete, mortar and plaster. English masonry worker Joseph Aspden patented Portland cement in 1824. It was named because of the similarity of its color to Portland limestone, quarried from the English Isle of Portland and used extensively in London architecture. It consists of a mixture of oxides of calcium, silicon and aluminium. Portland cement and similar materials are made by heating limestone with clay and grinding this product with a source of sulfate. In modern cement kilns, many advanced features are used to lower the fuel consumption per ton of clinker produced. Cement kilns are extremely large, complex, and inherently dusty industrial installations, and have emissions which must be controlled. Of the various ingredients used in concrete, the cement is the most energetically expensive. Even complex and efficient kilns require 3.3 to 3.6 gigajoules of energy to produce a ton of clinker and then grind it into cement. Many kilns can be fueled with difficult-to-dispose-of wastes, the most common being used tires. The extremely high temperatures and long periods of time at those temperatures allows cement kilns to efficiently and completely burn even difficult-to-use fuels. Water. Combining water with a cementitious material forms a cement paste by the process of hydration. The cement paste glues the aggregate together, fills voids within it, and makes it flow more freely. A lower water-to-cement ratio yields a stronger, more durable concrete, whereas more water gives a freer-flowing concrete with a higher slump. Impure water used to make concrete can cause problems when setting or in causing premature failure of the structure. Hydration involves many different reactions, often occurring at the same time. As the reactions proceed, the products of the cement hydration process gradually bond together the individual sand and gravel particles and other components of the concrete to form a solid mass. Reaction. Cement chemist notation. C3S plus HCSH plus CH. Standard notation. California 3CO5 plus H2O plus California 2 balanced. 2 California 3CO5 plus 7 H2O 324 plus 3 California 2 aggregates. Fine and coarse aggregates make up the bulk of a concrete mixture. Sand, natural gravel, and crushed stone are used mainly for this purpose. Recycled aggregates are increasingly used as partial replacements of natural aggregates, while a number of manufactured aggregates, including air-cooled blast furnace slag and bottom ash, are also permitted. The presence of aggregate greatly increases the durability of concrete above that of cement, which is a brittle material in its pure state. Thus concrete is a true composite material. Redistribution of aggregates after compaction often creates inhomogeneity due to the influence of vibration. This can lead to strength gradients. Decorative stones such as quartzite, small river stones or crushed glass are sometimes added to the surface of concrete for a decorative, exposed aggregate finish, popular among landscape designers. In addition to being decorative, exposed aggregate adds robustness to a concrete driveway. Reinforcement concrete is strong in compression, as the aggregate efficiently carries the compression load. However, it is weak in tension as the cement holding the aggregate in place can crack, allowing the structure to fail. Reinforced concrete adds either steel reinforcing bars, steel fibers, glass fibers, or plastic fibers to carry tensile loads. Chemical admixtures. Chemical admixtures are materials in the form of powder or fluids that are added to the concrete to give it certain Characteristics not obtainable with plain concrete mixes. In normal use, admixture dosages are less than 5% by mass of cement and are added to the concrete at the time of batching, mixing. The common types of admixtures are as follows. Accelerators speed up the hydration of the concrete. Typical materials used are CaCl2, California 2 and Nano 3. However, use of chlorides may cause corrosion in steel reinforcing and is prohibited in some countries, so that nitrates may be favored. Accelerating admixtures are especially useful for modifying the properties of concrete in cold weather. Retarders slow the hydration of concrete and are used in large or difficult pours where partial setting before the pour is complete is undesirable. Typical polyol retarders are sugar, sucrose, sodium gluconate, glucose, citric acid, and tartaric acid. Air entraining agents add and entrain tiny air bubbles in the concrete, which reduces damage during freeze-thaw cycles, increasing durability. However, entrained air entails a trade-off with strength, as each 1% of air may decrease compressive strength 5%. If too much air becomes trapped in the concrete as a result of the mixing process, defoamers can be used to encourage the air bubble to agglomerate, rise to the surface of the wet concrete and then disperse. Plasticizers increase the workability of plastic or fresh concrete, allowing it to be placed more easily, with less consolidating effort. A typical plasticizer is lignosulfonate. Plasticizers can be used to reduce the water content of a concrete while maintaining workability and are sometimes called water reducers due to this use. Such treatment improves its strength and durability characteristics. Superplasticizers are a class of plasticizers that have fewer deleterious effects and can be used to increase workability more than is practical. With traditional plasticizers, compounds used as superplasticizers include sulfonated naphthalene formaldehyde condensate, sulfonated melamine formaldehyde condensate, acetone formaldehyde condensate and polycarboxylate ethers. Pigments can be used to change the color of concrete. For aesthetics, corrosion inhibitors are used to minimize the corrosion of steel and steel bars in concrete. Bonding agents are used to create a bond between old and new concrete with wide temperature tolerance and corrosion resistance. Pumping aids improve pumpability, thicken the paste and reduce separation and bleeding. Mineral admixtures and blended cements in organic materials that have pozzolanic or latent hydraulic properties. These very fine-grained materials are added to the concrete mix to improve the properties of concrete, or as a replacement for Portland cement. Products which incorporate limestone, fly ash, blast furnace slag, and other useful materials with pozzolanic properties into the mix are being tested and used. This development is due to cement production being one of the largest producers of global greenhouse gas emissions, as well as lowering costs, improving concrete properties, and recycling wastes. Fly ash, a byproduct of coal-fired electric generating plants, it is used to partially replace Portland cement. The properties of fly ash depend on the type of coal burnt. In general, siliceous fly ash is pozzolanic, while calcareous fly ash has latent hydraulic properties. Ground granulated blast furnace slag, a byproduct of steel production, is used to partially replace Portland cement. It has latent hydraulic properties. Silica fume, a byproduct of the production of silicon and ferrosilicon alloys. Silica fume is similar to fly ash, but has a particle size 100 times smaller. This results in a higher surface-to-volume ratio and a much faster pozzolanic reaction. Silica fume is used to increase strength and durability of concrete, but generally requires the use of superplasticizers for workability. High reactivity metakaolin. Metakaolin produces concrete with strength and durability similar to concrete made with silica fume. While silica fume is usually dark gray or black in color, high reactivity metakaolin is usually bright white in color, making it the preferred choice for architectural concrete where appearance is important. Carbon nanofibers can be added to concrete to enhance compressive strength and higher Young's modulus, and also to improve the electrical properties required for strain monitoring, damage evaluation and self-health monitoring of concrete. Has many advantages in terms of mechanical and electrical properties and self-monitoring behavior due to the high tensile strength and high conductivity. Carbon products have been added to make concrete electrically conductive, for de-icing purposes.